Welcome to this explainer. You know, it's so easy to just think of Earth as a rock floating out there in the dark cosmic void. But today, we are going to look at it as a massive, hyper-connected engine. We'll uncover the energetic machinery that keeps our planet glowing and pulsating with life, starting with a really critical question about its future.
And we're kicking things off with a massive real-world mystery. What actually happens to our coastal cities if glaciers and polar ice just keep melting faster? Well, to figure that out, we can't just look at the ice. We literally have to peel back the foundational layers of our entire planet.
So here is our roadmap for today. We're going to dive into the interconnected spheres, how solar energy drives the system, our atmospheric shield, winds and matter cycles, and finally, human impact. Let's run a system diagnostic and get right into it.
Part 1. The interconnected spheres and the systemic domino effect.
Picture the Earth. First up, you've got the geosphere. That's all the solid bedrock, the deep amber soils, the Earth's interior. And seamlessly wrapping around that rock is the hydrosphere. This is the liquid stuff. Every ocean, river, lake, and even the hidden groundwater pulsing right beneath our feet.
Then, layer on the crystalline ice of the cryosphere, our glaciers and frozen poles. Wrapped around all of that is the wispy, protective gas of our atmosphere. And finally, tying the whole shebang together, the biosphere, that emerald green web of all living organisms. Humans, plants, marine life, we are all a part of it.
Now here's where it gets wild. A disturbance in just one of these spheres sends a massive shockwave rippling through all the others. It's a literal domino effect. Check out this chain reaction. Say you get a really mild winter with less snow in the cryosphere. Well, come summer, that means way less meltwater flowing into the hydrosphere. Because of that, less grass grows in the mountains, and suddenly, sheep in the biosphere starve. See? Completely interconnected.
Moving on to part 2, solar energy and heating, fueling the Earth engine.
Okay, so what actually powers this massive 3D system? What keeps the engine running? It's our ultimate off-screen powerhouse, the sun. Intense golden solar radiation shoots through the pitch-black void of space at an absolutely staggering speed, 300 million meters per second. That is the speed of light, and it doesn't even need a medium to travel through. It just punches straight through the cosmic dark.
So, the really crucial thing is how much of that intense energy actually hits us. To put a number on it, 1.4 kilowatts per square meter. Scientists call this the solar constant. Just imagine a 1 square meter box hovering at the very top of our atmosphere. Every single second, it gets blasted with that exact average amount of raw solar energy. But when that light finally hits the ground, what happens next depends entirely on something called albedo. Basically, it's how reflective a surface is. High albedo stuff, like bright white snow, bounces 80 to 90% of that light right back into space, staying perfectly cool. But low albedo materials, like crushed rock or dark concrete, they just absorb that light like a sponge. This is exactly why a city packed with concrete absorbs heat all day and turns into a sweltering urban heat island at night, while the countryside stays cool.
Right, let's head into part 3, the atmospheric shield, our glowing thermal blanket.
Before that intense solar radiation even has a chance to reach the surface, it has to pass through Earth's invisible shield. Held tight against the planet by gravity, this atmospheric layer has a wildly specific recipe. We're talking 78% nitrogen and 21% oxygen. That leftover 1%, that's argon, carbon dioxide, and water vapor. It sounds tiny, I know, but that 1% is absolutely critical to keeping our entire planet alive.
If we look closer at these atmospheric strata, the dynamics are fascinating. Down in the troposphere, from 0 to 12 kilometers up, the temperature drops the higher you go, and that's where all our volatile weather and dark storm clouds form. But cross into the stratosphere above it, everything flips. It actually gets warmer. That's because the ozone layer up there is violently intercepting and absorbing harmful ultraviolet rays, acting as this incredible neon blue protective shield for us down below.
Meanwhile, down in that lower atmosphere, certain molecules act literally like a giant thermal blanket. Here's how it works. Earth absorbs sunlight and then tries to radiate it back out into the dark void as infrared heat. But greenhouse gases, like CO2 and methane, trap a lot of that heat. Without this, Earth would be a frozen ice ball. But if this process spirals out of control, well, you get Venus, an atmosphere so thick it traps endless heat, making it hotter than Mercury, even though it's farther from the sun. Yikes.
Which brings us to part 4, winds and matter cycles.
the biospheric conveyor belts.
Because the Earth is, a curved sphere, that incoming solar heat doesn't hit evenly. We get this intense, concentrated heat at the equator and much weaker, spread-out heat at the poles. These massive temperature differences create global pressure zones. And wind? It always flows from high to low pressure. But since the Earth is spinning, those wind streams get bent, to the right in the north and the left in the south. We call this the Coriolis effect. And this exact same rotational force drives massive ocean currents called gyres. The Gulf Stream is a perfect example. It carries so much warm tropical water north that it literally keeps European ports completely ice-free in the dead of winter. How cool is that?
But it's not just wind and water moving around. Chemical matter loops dynamically through the system too. Think about the nitrogen cycle. Our atmosphere is absolutely loaded with nitrogen gas, but plants can't just absorb it. So microscopic bacteria in the dark soil act like nature's chemical transformers. Through fixation and nitrification, they pull that inert gas right out of the air, convert it into usable biological building blocks, and eventually release it back. It is a seamless, endless planetary loop. And that leads to our final section, Part 5, Human Impact and Balance, a Dystopian Shift. Now we have to take an objective look at how human activity is sending a warning pulse across this fragile grid. Driven heavily by industrial emissions and mass deforestation, atmospheric carbon dioxide has jumped dramatically. We're talking 315 parts per million in 1960 to roughly 420 today. That is a 35% spike in just a handful of decades. Basically, we're pumping CO2 into the air way faster than the natural carbon cycle can lock it back down, significantly thickening that thermal blanket we talked about earlier.
At the exact same time, we're mass-producing artificial nitrogen fertilizers to grow crops. And when that agricultural runoff washes into our lakes and rivers, it triggers something called eutrophication. This causes huge, explosive blooms of algae that quite literally choke the life out of aquatic ecosystems by sucking up all the dissolved oxygen. It suffocates marine biodiversity.
And all of this brings us full circle to the mystery we started with. Our oceans act as a massive buffer, absorbing about 71% of the globe's excess carbon. But as those seas absorb the warming shock, evaporation spikes. This totally disrupts global monsoon systems, causing severe floods in some regions and brutal droughts in others. Most critically, this atmospheric warming accelerates the melting of our cryosphere. The glaciers melt faster, the deep blue seas rise, and suddenly, the habitats of coastal cities are in immediate physical danger.
So as you can see, everything in the Earth system is deeply, intricately connected. A shock to the atmosphere creates a direct disaster in the biosphere. As we wrap up this explainer and the planetary grid fades to black, I want to leave you with a critical question. Knowing how delicate this balance is, what sustainable habits can you adopt today to help stabilize our planet's life support system? Think on that, keep learning, and I'll see you in the next explainer.